you have indeterminate form, so if you end up with 0 over 0, and you're looking at either one-sided limits or limits at infinity, you can still apply L'Hopital's rule to evaluate the limit. So if the limit as x approaches c to the right or to the left of f of x over g of x gives you 0 over 0, then again, you can take the derivative of the numerator, the derivative of the denominator, and then find the limit. Or if you're going to positive or negative infinity, the same thing can happen. So let's continue on. So let's find the limit as x approaches 0 from the right of x over the natural log of x plus 1. Again, always start with direct substitution. So 0 over the natural log of 0 plus 1. So you're looking at 0 over the natural log of 1, which is 0 over 0. That's indeterminate form. So we're allowed to use L'Hopital's rule. Well, L'Hopital's rule says if you want to find a limit and you're looking at a limit from the left or the right, a limit at positive or negative infinity, or a limit at the number, and you ended up with indeterminate form, you can find this limit by finding the derivative of the numerator. Well, the derivative of x is 1 divided by the derivative of the denominator. Well, the derivative of the natural log of x plus 1 is the derivative of x plus 1, which is 1 over x plus 1. And then we take the limit again. Well, let's clean this up before we take the limit again. So now recall that this is the same as me saying 1 divided by 1 over x plus 1. And if you're dividing by a fraction, it's the same as multiplying by the reciprocal. Well, the reciprocal of 1 over x plus 1 is going to be x plus 1 over 1. So we're really just looking at the limit as x approaches 0 from the right of x plus 1. So direct substitution, 0 plus 1 equals 1. Let's go to the next one. The limit as x approaches negative infinity. So I need to figure out what the limit as x approaches negative infinity of the natural log of 1 plus 2 times e to the x all over e to the x is. So direct substitution yields the natural log of 1 plus 2 e to the negative infinity all over e to the negative infinity. Recall from what we said at the beginning of this section, e to the negative infinity is actually going to 0. So if we go back here, e to the negative infinity is actually going to 0. So the limit as x approaches negative infinity of e to the x is going to equal 0. So that's going to be the natural log of 1 plus 2 times 0, because again, e to the negative infinity is 0, all over 0, which is just the natural log of 1 over 0, which is 0 over 0, which is my indeterminate form. So I know that I can use L'Hopital's rule. So you have to be in indeterminate form in order to use L'Hopital's rule. So let's go ahead and use L'Hopital's rule now. So L'Hopital says what we can do is take the derivative of the numerator. Well, what's the derivative of the natural log of 1 plus 2 to the x? Well, it's going to be whatever the derivative of 1 plus 2 e to the x is. Well, the derivative of 1 plus 2 e to the x is just going to be 2 e to the x all over the function 1 plus 2 e to the x divided by the derivative of e to the x. Well, the derivative of e to the x is e to the x. And now if we clean this up, again you're looking at the limit as x approaches negative infinity of 2 e to the x over 1 plus 2 e to the x divided by e to the x. And if you're dividing by something, it's the same as multiplying by the reciprocal. So you're looking at 2 e to the x all over 1 plus 2 e to the x times 1 over e to the x. And these e to the x's cancel. So this is just the limit as x approaches negative infinity of 2 over 1 plus 2 times e to the x. So direct substitution now, we get 2 over 1 plus 2 times, remember the limit as x approaches negative infinity of e to the x is 0, so this ends up being 1 plus 0, or just 1, so 2 over 1 is just 2. So the limit as x approaches negative infinity of the natural log of 1 plus 2 to the x over e to the x is equal to 2. Let's look at one more thing that we can get and use L'Hopital's rule for. So we know that we can use L'Hopital's rule anytime we end up with 0 over 0. But now I'm letting you know that other indeterminate forms are infinity over infinity or negative infinity over negative infinity. So whenever you have plus or minus infinity over plus or minus infinity, that's also indeterminate form. And if you end up with that, you can use L'Hopital's rule to evaluate the limit. So let's look at example 9. Find the indicated limit. So if I have limit as x approaches infinity of 6x minus 7 over 5x plus 1, well, I know 6 times infinity is just going to be infinity. Minus 7 is still going to be infinity. And I know that 5 times infinity is going to be infinity. Plus 1 is just still going to be infinity. So this is infinity over infinity, which means I can use L'Hopital's rule to figure out what the limit is. So what it tells me to do is take the derivative of the numerator. Well, the derivative of 6x minus 7 is just going to be 6. And the derivative of 5x plus 1 is just going to be 5. Therefore, the limit as x approaches infinity of 6 over 5 is going to be 6/5. Let's look at example number 10. So the limit as x approaches negative infinity of x to the 4th minus 5 over x squared plus 4. So what we're doing here is, again, looking, if I take a negative infinity and raise it to the 4th power, it becomes positive infinity. If I take a negative infinity and raise it to the 2nd power, it becomes positive infinity. Again, subtracting 5 and adding 4 isn't really going to make a difference there. Well, this is infinity over infinity, which means that I can use L'Hopital's rule. Well, L'Hopital's rule says take the derivative of the numerator. Well, the derivative of my numerator is 4x cubed. And take the derivative of my denominator. Well, the derivative of my denominator is 2x. And then take the limit again. But just like all the other problems we've done, let's clean this up before we take the limit. Well, notice that 4 over 2 will reduce to 2, and x cubed over x is just x squared. So we're really looking at the limit as x approaches negative infinity of 2x squared. Well, this ends up being 2 times positive infinity, because negative infinity squared is positive infinity, so the limit here is equal to infinity. Let's look at number 11. The limit as x approaches infinity of e to the 3x over x cubed. Same thing, we're looking at e to the infinity over infinity cubed, which is just going to be infinity over infinity. Because recall from the beginning of the section, if you're looking at the limit as x approaches infinity of e to the x, that's going towards infinity. So, infinity over infinity means use L'Hopital's rule. And L'Hopital says you want to find this limit, what you can do is take the derivative of my numerator, which is e to the 3x times 3, and divide it by the derivative of the denominator, which is 3x squared. Well, my 3's will cancel, so this is the same as the limit as x approaches infinity of e to the 3x over x squared. Well, if I try direct substitution again, I end up with e to the infinity, which is infinity, and infinity squared, which is infinity. So I'm allowed to use L'Hopital's rule again. So using L'Hopital's rule, I get the limit as x approaches infinity of, well, the derivative of e to the 3x is e to the 3x times 3 over the derivative of x squared is 2x. Nothing cancels, and so we end up with infinity over infinity again when we try direct substitution. So L'Hopital's rule says try it again. Take the derivative. So we're looking at the limit as x approaches infinity of, well, 3 is a constant multiplier. Remember, it multiplies along. So 3 times the derivative of e to the 3x is e to the 3x times 3 all over. The derivative of 2x is 2. So if I clean this up real quick, we're looking at the limit as x approaches infinity of 9 e to the 3x over 2. So this is going to be infinity over 2, which is infinity. So the limit as x approaches infinity of e to the 3x over x cubed is actually infinity. Let's look at the last one in this section. And the last one in this section is the limit as x approaches -3 of x squared over x plus 3 to the fifth. So the very first thing that we do is always try direct substitution. So we have -3 squared over -3 plus 3 to the fifth. So we're looking at 9 over 0 to the fifth, or 9 over 0. This is not indeterminate form. Well, if you are not in indeterminate form, remember we used the graph of this to figure this out. So if we grab our calculator and graph this, on our graphing calculator, hit your y equals, and then put in x squared divided by x plus 3 to the fifth. Press graph, and we're trying to figure out what happens at -3. Well, what's happening at -3? Well, if you look here, the limit from the left is going towards negative infinity, and the limit from the right is going towards positive infinity. So this limit does not exist. So the way that we could find that, right, if we didn't use the graph, is look at the limit as x approaches -3 from the left of x squared over x plus 3 to the fifth. And remember what we would do is we just plug in direct substitution in our numerator. And then we'd plug in a number that is to the left of -3, but pretty close to -3. And then we notice here we'd end up with positive 9 over, and this would be a negative tiny number, so we know this was going towards negative infinity. And then the limit as x approaches -3 from the right, again this is x squared over x plus 3 to the fifth. So -3 squared over a number that's to the right of -3 but pretty close to -3. And we'd end up with 9 over a positive tiny number, which is positive infinity. And since the limit from the left and the limit from the right did not agree, we know that this limit does not exist. Or again, you can look at the graph and just determine, hey, the limit from the left goes to negative infinity, the limit from the right goes to positive infinity, so that limit does not exist. That's it for section 4.3.